So we're going to be starting something new today, and I'm going to try not to use my teacher voice. Chloe tells me that I talk funny when I'm doing these videos, so I'm going to try to talk in my normal voice, but I forgive you. Y'all just have to forgive me for having to listen to me. I wish we were back at school. I missed you guys so much. Okay, today we're going to talk about cell transport. And if you want to go ahead and pull up the copy of your cell transport notes that you have on Google Classroom as I'm going through this PowerPoint, maybe if you do like a split screen, you can fill in your notes as we're going over this. But, okay, first of all, we want to look at the cell membrane. The cell membrane, when we talked about the cell, is what surrounds the cell and controls what gets to go in and out of the cells. And this is a very zoomed in picture of the cell membrane. And so this would be like all along the outside of the cell. And this is all on the inside of the cell. And so you can see that there are two layers here. We've got a layer on this side and a layer on this side. And they're made of these materials called phospholipids. That's phosphates and fats. But you don't really have to focus on that. But it is selective in what it allows to go across the membrane. So if I'm selective in who I let be in my class, that means that I don't let everybody in. Only certain people get to come in. Well, that's what it's like with the cell. Only certain things can come across into the cell, and only certain things can go back across and leave the cell. All right, and we're going to look at some different types of cell transport. The first one is simple diffusion. This can be where it does not require any energy. In other words, this is going to happen on its own without us mixing the solution or stirring it or doing anything to it. So let's assume that you put a drop of food coloring here in a container. Is it going to stay right there all in that one little drop? No, it's going to start moving out to where there is less of that food coloring, and before you know it, you've got little particles or little molecules of the food coloring all throughout the water. All right, I guess I should have changed that to purple, but we would have the purple spread all throughout the container. So what happens is it goes from an area of high concentration to low concentration. So that little drop was highly concentrated right there in the drop, and it was less concentrated out here where there wasn't. And so it moved from this highly concentrated area here out to the less concentrated areas. All right, again, remember that diffusion is passive, which means it does not require energy. It has a natural kinetic energy. That means it's going to move on its own. So, for example, if we were looking at this cell here, here's a cell, and we're going to say that there's some particles that need to move across the cell. Well, it's highly concentrated outside the cell, and it's less concentrated inside the cell, so these little particles would move in. All right, this is just an illustration about the food coloring that we just talked about. Here it is, highly concentrated in the drop, less concentration out here, and you're going to see it moving in all directions until it gets to this thing that we call equilibrium. That means that it's evenly distributed throughout. All right, in osmosis is just a special type of diffusion. So it's still diffusion. So it still means that things are moving from high to low. It does not require energy. And it is passive also, which is, that also means doesn't require energy. But what we're looking at is not just the diffusion of any molecule like we saw over here. This could have been salt, this could have been sugar, it could be any kind of molecule that was moving across the cell. But in osmosis, the water is what's moving. So the water moves from high to low. And hopefully this will make more sense in just a minute. So if you look at this picture, you've got some solutes, which are little particles that are dissolved in the water, and those are the green dots, okay? And you've got those on both sides of the membrane. But then these little smaller molecules, those are your water molecules, H2O. All right, so we've got the left side and the right side. If you were going to decide which way the water was going to move, can you guys see that there's a lot more waters on the left side than there is on the right side? So the water concentration is high on the left and low on the right, so that causes the water to move to the right. Now, if I had been asking about the solutes, the green dots, are higher on the right and less on the left, and so the solutes would move to the left. But in this case, we're talking about the water. So make sure you're paying attention if the question is asking you about osmosis, which is going to be which way the water is going to move, or if the question is asking you about the solutes, which would be diffusion, which way those little particles are going to move. Okay? So there's 3 types of osmotic solutions. In geometry, or if you've done a little bit with geometry in your algebra classes, you probably have learned about isosceles triangles. And this first term begins with that prefix iso. And iso simply means equal, like an isosceles triangle has equal sides. An isotonic solution has equal concentrations inside and outside the cell. So again, remember in osmosis, we're looking at the water. So we've got 90% water on the outside of the cell, 90% water on the inside of the cell. And so we say the cell is at equilibrium. There's a balance. It's equal inside and out. But a lot of people want to say that the water will not move in either direction, and that is not true at all. That's why we've got 2 arrows here. Water will actually move out and in. It will move in both directions in an isotonic solution, but overall there's no change. So if I had 2 molecules that went out, then I would have 2 molecules that came in, so we're still keeping the balance. So however many molecules of water go out, the same number come in. But if the question were to ask you what direction does water move in an isotonic solution, it's going to move in both directions. All right, in a hypotonic solution, well, wait, let me, back on your notes, it asks you to draw in some information about the picture there. So it may be a little bit hard to do. So you may, on the notes page, you may just be able to fill in the blanks, and you may not be able to type inside the boxes. I'm not sure about that, because originally this was, we would have written this down in class. So again, now we're moving on to the second kind of solution, which is hypotonic. Okay, that means lower solutes outside the cell. So remember, the solutes are the little particles that are dissolved in the water. But for osmosis, we have to look at the water to see which way the water is going to move. So here we have 90% water outside the cell, 80% water inside the cell. So you got to ask yourself, where is the water high? 90 is higher than 80, so the water is high on the outside and low or lower on the inside. So which way is the water going to move? It's going to move into the cell because it is high on the outside, low on the inside. In osmosis, the water always moves from high to low. And so in a hypotonic solution, water moves in and the cell will swell. So what happens here is as water rushes into this cell, it's going to get really big. It's going to swell up. And the way I remember what happens to a cell if it's placed in a hypotonic solution, here's my Eastern Kentucky twang coming in. We used to use the terminology like, well, that's a big old snake, or that's a big old tire, or something like that. Well, in a hypotonic solution, it's going to make a big old cell because the water moves in. So I know that's kind of funny, but it hopefully will help you to remember it. All right, and then the last type is a hypertonic solution. Hypertonic. So this is where the solutes are higher outside the cell than inside the cell. But again, to find out which way the water moves, you got to ask yourself, where is the water high? Where is the water low? So when we're looking at the water concentration, it's high on the inside because we've got the 90% water. And it is lower on the outside because we've got the 85% water. So if water moves from high to low, it's going to go out of the cell. So if we pull water out of the cell, instead of it getting bigger, what do you think is going to happen? It's going to shrivel up and kind of shrink. So in a hypertonic solution, the cells shrink. So I don't have a cute little way to remember that, but if I can remember hypo is the one that swells, then I can know that hyper is the one that's opposite, and it's going to cause it to shrink. It pulls the water out. All right. All right, here we're going to label, it asks you to label the pictures. It says the drawings below show the appearance of a red blood cell and a plant cell in isotonic, hypotonic, and hypertonic environments. Label each of them. So in the red blood cell, let me kind of go back to this picture here. Normally red blood cells are kind of sunken in the middle right here, so they kind of look hollow. So when it is in a hypotonic solution, it doesn't look sunken in anymore. It looks really puffed out and swollen. Here, though, in the hypertonic, you can see it's kind of like shriveled up. Okay? So when we go back over here, because this one is really swollen and you don't see that little indentation anymore, that tells us it's the hypotonic because it made a big O cell. Isotonic, remember, that's when everything's in balance. And so this is what the cell should normally look like. But in the hypertonic solution, remember that causes the water to move out. And so the cell has kind of shriveled up and pulled in on itself and shrunk a little bit. Now, the plant cell is just a little bit different because it has the cell wall. And so that helps it to keep its shape a little bit more. But this is where like the cytoplasm has kind of pulled away from the sides. And so the water has actually gotten pulled out of these cells, which makes it a hypertonic solution. Isotonic, this is what the cell would normally look like when everything's in balance. And then notice in the hypotonic one how the edges are kind of bulging out. That shows you that there's been a lot of water that got pulled in here, and so it's really swollen up. One thing I forgot to mention here is that in animal cells, if the hypotonic solution is strong enough and this thing swells big enough, it can cause the cell to burst. Okay, now we usually don't see plant cells bursting because, again, they've got that cell wall, and that's what causes the to keep that pressure in there, but it doesn't let it burst because it's got that extra support. All right. Now, that's the end of the notes page, but you've also got a practice page. And on the practice page, you've got a little chart that you're going to mark if the statement goes along with an isotonic solution, a hypotonic solution, or a hypertonic solution. But then in part 2 on the osmosis practice, it asks you to figure out what kind of solution the cell has been put in. So this is number 1, or actually number 11 on the practice problems. So it gives me the percent of the solute. So remember, the solute are the little particles dissolved in the water. So my solution has to add up to 100%. So if I have 100% solute outside the cell, then my water concentration has to be 85% water. All right. If on the inside of the cell, if I've got 10% solute, then I have to have 90% water. So if I've got to figure out what direction the water is going to move, remember that water in osmosis moves from high to low. Well, the water is higher on the inside of the cell because it's 90. It's lower on the outside of the cell because it's 85. So if it moves high to low, the water is going to move out of the cell. So if the water moves out, the cell will shrink. And we know that that is a hypertonic solution. So you're going to work some problems similar to that on the practice. And then you got some real life application questions that go along with it for those last 3. It kind of makes you think a little bit more with those last questions, 15, 16, and 17. All right, I'm going to hop off of here. If you guys have any questions, remember that you're welcome to email. And I'm going to probably be setting up a Google Hangouts for us to be able to go over any questions. So I'll get back with you with some more information about that.